Hi, Assalamualaikum and hello to Dr. Arif. We are from Group 1, consists of me, Ahmad Afif Jazimin, Lim Kai Peng, Lau Jiro and Muhammad Nazri. Of course, Thermodynamics and Mechanics of Material Laboratory. So we are going to present our experiment 3, which is vapor compression refrigeration. The first part is introduction. The objective of this experiment to determine the coefficient of performance COP for vapor compression cooling system. The scope of this experiment: refrigerator is devised to transfer heat from low temperature to high temperature. In this experiment, we use water as a fluid with large thermal mass. Then the values of QH and QL will use to calculate the coefficient of performance COP. And the last one, the data will be recorded by constant flow rate evaporator at 25 grams per second and changing flow rate condenser for 5 times.
I will present about the theory for this experiment. There are four parts involved in the typical refrigeration cycle, which are compressor, condenser, expansion bath, and also evaporator. In this experiment, the cooling system receives heat from the low temperature region and transfer to the high temperature region through the refrigeration cycle. The process requires work W to be supplied to the system. This is because of the vapor compression refrigeration cycle against the second law of thermodynamics, which is heat can never pass to a warmer body from a colder body without any other change. In this experiment, the formula we apply is coefficient of performance, COP, equals to cooling effect divided by work.
So this is our experimental setup. As we can see in the figure 2, in the left side we have a condenser and the right side is evaporator. And then we have a flow rate meter, then compressor, watt meter and valve. And the last one we have temperature 1 until temperature 7 for record in the table.
To start the experiment, firstly, valve for condenser and middle valve was open. Step 2, the water pipe was open and the water flow to the evaporator was set to 25 gram per second and the water flow rate to the condenser to maximum. Step 3, the main switch was open. Step 4, the cooling system was allowed to be stable in about 10 minutes and the parameters were recorded. The experiment were repeated for 4 times by changing the flow rate for condenser for 35 to 40 gram per second. To terminate the experiment, the main switch was set down, the water supply was then turned off, and close the valve for condenser and middle valve.
The table shown below is the data for vapor compression refrigeration. We will now calculate the rate of heat transfer that occurs in the evaporator and the condenser for 5 test runs and discuss the results. Both the rate of heat transfer at evaporator and condenser are mostly similar, just that the temperature refer are different part. Once we obtain both the rate of heat transfer, we can find our coefficients of performance. Now I will show the example on how to obtain the first run of rate of heat transfer at evaporator. Based on the table 5.1, we can get that the mass flow rate of water at evaporator T1 and T2. Then we sub all the values into the formula where m dot times Cp times delta T, we can get our rate of heat transfer, where Cp is the specific heat capacity of water. The following is the example on how to obtain the first run of rate of heat transfer at condenser. The steps are similar to the previous one, just that the temperature we are referring is T3 and T4. Once we obtain both the Q1 and Q2, we can get our COP, which is a positive value. By applying the same steps to find Q1, Q2 and COP for the 5 test runs, we can complete our table as shown below. You may pause the video to go through the data. Based on the previous page table, we can see that the rate of heat transfer at evaporator is higher than condenser. For evaporator, since heat is added to the liquid and change its states from liquid to vapor, the rate of heat transfer become a positive value. This is because of the large separation of the particles in the gas states. More energy is required. For condenser, the heat is removed from the gas and change its states to liquid. That's why the rate of heat transfer is negative value. The graph shown below is the graph of compressor power input against condenser flow rate. Based on the graph 5.1, we observe that when the condenser flow rate increase, the compressor power decrease. Besides, when the flow rate increase, it allows the refrigerant to lose heat more quickly. This leads to the decrease in power input, since less work to be done by the compressor to the refrigerant.
Conclusion. The process requires works W to be supplied to the system as the vapor compression system against the second law of thermodynamics. Heat can never transfer from a colder region to a hotter region without any changes. From the result obtained, we could learn that when the flow rate of the condenser decreases, the condenser power input increases. This leads to more work is needed to be done in order to reach the cooling effect. To avoid any mistake or inaccuracy of the data, we have to ensure the level of reading is correct before the experiment is conducted. Procedure. Firstly, we have to avoid touching the surface of the demonstration unit during the experiment. This is because the surface of the condenser is hot. We have to avoid the potential to be scheduled by the demonstration unit. Secondly, we have to follow the instruction of the experiment procedure. This is to avoid damaging the demonstration unit and also avoid releasing the toxic gas, which is furan R141B. It will cause heart irregularity, unconsciousness, or death if inhaled. Lastly, we have to report any injury to the lab assistant to get the immediate first aid treatment if there is any injury happens.
This is our reference throughout this experiment.
This is our appendix, which are the data obtained during the experiment. Thank you for watching.